Right, topic 5, forces. It's a reasonably short topic dealing with equilibrium and to do with forces, and then also equilibrium to do with moments or the turning effect of a force. So first of all, just to talk about equilibrium. Equi meaning equal. Equilibrium are situations where um, the forces or perhaps the moments on an object are balanced. And if that is the case, then we can say that there is going to be no acceleration, either a linear form of acceleration or rotational. So that's a very general definition of equilibrium. So we've got a few little pictures here of bodies that are in equilibrium. Now that first one on the top left here looks a bit unlikely, but assuming that this rock that's sitting up there manages to stay there and doesn't slide down or doesn't topple over, if it actually stayed there in a balanced position, then that rock would be in equilibrium. Similarly, for this particular one here, provided somehow it could balance there, we would say it's in equilibrium. This dice sitting on a bench top is in equilibrium. It's not ready to slide sideways or go up or go down or to rotate. So I want you in your notes to write down that definition of equilibrium first of all. All right, now one of the conditions for an object to be in equilibrium is stated here. All right, a point or an object, which at this stage we're just going to consider to be like a single point. We'll get to the dealing with a larger body later, that a point object will be in equilibrium if the algebraic, now your dictionary says the algebraic sum of the forces acting on it is zero. For myself, in terms of my own understanding, I think I would prefer to think of it as being the vector sum, because we know that force is a vector. So even though it says algebraic sum, in terms of practical understanding, it's really that the sum of the forces, taking into account their vector nature, adds up to zero. So on the left-hand side here, we've got a fairly simple little situation where we've got then a point object, and there are just the two forces acting on that object. We've got 10 newtons upwards, 10 newtons downwards. So the sum of the forces acting on that point is zero. All right, this if you're not certain, that sigma there means sum of, Greek letter capital sigma. Sum of the forces acting on the object is zero. And here is just a little statement that says what we mean by a point object. Has no physical size. It's just sort of really sort of almost an imaginary or thought object that we're dealing with at this point. So in terms of your notes, I want you to write down the statement up here, the condition for equilibrium, and I think just take a little note to yourself about the vector nature and that statement there, plus this little example on the left-hand side. All right, just a couple of things just to illustrate what we've just been talking about then. So if you've got this block here and we're applying a couple of forces to it, I just want to mention the word tension. In some of the assignment questions, we've used the term tension already, and people have been asking what we mean by the term tension. Tension is simply a force being applied to something, trying to stretch it. So it's the type of thing that you can apply to a rope or to a wire. You can never push on a rope, you can only pull on a rope. So in this diagram up here, we've got this block. If we apply a force there of, let's say, 100 newtons, then for this block to remain stationary, there must be a force acting there of 100 newtons as well. Now, you'll find in, I think, in your assignment questions, there's a question about tug of war. If you've got a bunch of people pulling on a rope one way with a force of 1,000 newtons, for that rope not to move, then this group must also apply force the other way of 1,000 newtons. Now, it doesn't matter whether it's a bunch of people pulling on this left-hand end, or if you tied that rope to a wall and pulled on it in one direction, the tension force would be the same. And something to realize is that that tension force is going to be the same right along the length of that rope in that direction, and you could argue in that direction as well. All right, now in terms of this page, nothing I think that I want you to write down. It's simply just a little bit of an explanation about tension. If you need to note anything for your own benefit, you can do so. All right, now let's deal with three forces in equilibrium. So we've got three forces here acting still on a single point up there. Just there, there's a single point there with forces acting on them. Let's see what needs to be the condition. We said before that the sum of the three forces must be 0. And we also said that that sum is a vector sum. All right, so let's just duplicate each of these lines, if I can do that, clone it, and just drag that down here somewhere. Let's take this one, clone it, drag it down here, take this one, clone it, drag it down here, put them together. Hey, presto, if I've done that, I haven't quite got it right, I don't think. Oh yeah, not too, it's a little bit faulty in terms of where I've put things, pretty close. I maybe haven't quite got things perfect. Maybe that's got to come in there a little bit of cheating there. Okay, but now what we've got is we've got one force, second force, third force. Take note that I've added those three forces together, head to tail, head to tail, head to tail. If you go round the triangle, they all go round in the same direction. That is what we call a closed triangle. All right, so if you've got three forces, if you add those three force vectors together and you get a closed triangle, then we know we have got those forces in equilibrium. So I'd like you to write the heading. I'd like you to draw an example like that. You may find it easiest perhaps to create the triangle first, and then having created the triangle, then copy those three forces to the top diagram so that the lengths of those three vectors match each other. All right, on this page here, this refers to a little practical that we'll do in class. I'd like you, please, just to write the heading force table example, and we'll list the three things: mass, force, angle, mass, force, angle, mass, force, angle, and we will create then in class, we'll do this, we'll create a vector diagram to see if we do get equilibrium happening at that particular point.